going to be discussing Chapter 1 of the Physics for Scientists and Engineers textbook by Sir Wayne Jewett, called Physics and Measurement. Within physics, we have very consistent quantities. We call these our fundamental quantities, which are variables of length, time, and mass, considered to be, so you can have meters, seconds, kilograms. Meanwhile, most of the variables that we will encounter within physics are derived quantities, which are expressions of the fundamental quantities. Examples of derived quantities are acceleration, velocity, force in newtons, kilograms times meters per second squared. That kind of stuff is all within the realm of derived quantities. Within physics, we have a tool called dimensional analysis, and this is to be used to make sure that a specific equation matches the expected results. This can be done because dimensions can be treated as algebraic quantities. So let's go through a dimensional analysis example. Show that the expression v equals at, where v is the velocity, a is the acceleration, and t is the time, is dimensionally correct. To start, you write down the dimensions for velocity, which is length over time. Then you've got your dimensions for acceleration, which is length over time squared, and your dimensions for time, which is just time. Eventually, you will multiply out, so you have your equation v equals at, so you've got length over time squared times time. The time will cancel with one of the times on the bottom of the equation, so you will be left with v equals L over t, which is correct dimensionally. So the expression v equals at is correct. Now, unit conversion is a type of dimensional analysis that allows you to convert from one set of units to another by known ratios. Rather than using our dimensional quantities, time, mass, and length, we will be using units, kilograms, feet, inches, centimeters, etc., whatever you want to choose. Here's an example of unit conversions. So you have a car traveling at a speed of 38.0 meters per second. Is the car exceeding the posted speed limit of 75 miles per hour? Here's the solution. So first, you will convert the meters in the speed to miles. So you have 38.0 meters per second, and your ratio for 1 mile is equivalent to 1,609 meters. Those meters on the bottom cancel, so you are left with 2.36 times 10 to the negative second miles per second. But that's not the answer that we need. We need to convert those seconds into hours. And to do that, you will take your value, 22.36 times 10 to the negative 2 miles per second. 1 second, 60 seconds is equivalent to 1 minute. 1 minute is 60 minutes is equivalent to 1 hour. So you will multiply 2.36 times 10 to the negative 2 times 60, which leaves you with 85.0 miles per hour. So this car is actually speeding, and they are going 10 miles per hour above the posted speed limit. Now, another tricky thing is significant figures and how to determine how many are in a specific value. Significant figures, or sig figs, as they are commonly called, are a way of expressing the uncertainty within a measurement. However, with this, there comes many rules to know how many sig figs are within a measurement and how to use those measurements within calculations. So how do you determine the number of sig figs in a value? Non-zero digits are always going to be significant. So no matter what, as long as it's not a zero, it's always considered significant. Now, any zeros between two significant digits are significant. So say you have 101. So that in there is going to be 3 significant figures because that zero in the middle is considered significant. And now finally, a final zero or trailing zeros in the decimal portion only are significant. So you have 0.500. The zeros are significant. But in the second example, 0.006 or 0.000968, the zeros are not significant. That is because they are preceding the significant digits. Now, we also have sig fig rules for addition and subtraction, multiplication and division. Within these, this is how you get, because most of our measurements aren't going to be just cut and dry. You're going to have to do some calculations. That's the nature of physics. Physics is just applied mathematics. So within this, you've got your addition and subtraction rules. So count the number of significant figures in the decimal portion only of each number in the problem. Then you're going to add or subtract in normal fashion, but your final answer can have no more significant figures to the right of the decimal point than the least number of significant figures in any number in the problem. So say you start with a value of 1.12 and you want to add that to 1.2. So you get 1.12 times 1 plus 1.2, you get 2.21, but your answer can only contain the least number of significant figures. So that will give you an answer of 2.2, not 2.1. And then you've got multiplication and division, where the least number of significant figures in any number of the problem determines the number of significant figures in the answer. So the difference between multiplication, division, and addition and subtraction is addition, subtraction, you're looking to the right of the decimal points. So anything, so you got 6.712, but in multiplication and division, you were looking at the total number of the significant figures. So so in that example 7.12, and if you're adding it, you would only be looking, you can only have a number with two numbers after the decimal. But multiplication and division, you can have a maximum of 3 total significant figures. It's just a little difference within it. I hope you all have enjoyed this today and have a wonderful day.